Hello, I hope all of you can hear me.
Yes, sir.
So please confirm that you can see the presentation.
Yes, sir.
Okay, thank you. So today I may take a little extra time, 5 minutes or so, because first I have to finish the discussion of these topics, which should be a part of your syllabus, and then maybe we can discuss a little bit about the exam strategy and everything, or even a few things about the lab next week. So please bear with me. So maybe today I'll take about 5 minutes extra to start with. Okay, so but let us resume the discussion that we had last week. The last topic on which we ended. Remember, we were discussing. I mean, all throughout we have been discussing uh, uh, motion of objects through a fluid medium. First, we talked about a particle falling through a long liquid column. Second, we talked about a particle falling through a long air column. Third, we talked about a bicycle rider's motion through air, that is horizontal motion. The first two were vertical downward motion. Then we talked about a horizontal motion. Now we are talking about projectile motion, where you have both a horizontal component and a vertical component. So that is the thing that we ended on in the last class. We talked about projectile motion. Initially, our discussion has been kept simple. We simply, I mean, we did not account for air drag. That will add its own complications. So without air drag, so the horizontal equation of motion is d2x dt squared is equal to 0. Let me just revise a few of those ideas. The vertical, in the vertical direction, the equation of motion is d2y dt squared is equal to minus g. And minus g meaning it's going up, but its gravity is acting downwards. So, so this is basically the way things happen. Initial velocity of projection is at an inclination angle of alpha with respect to the horizontal direction. And as such, and the initial projection velocity is v naught. Therefore, the horizontal component of the initial velocity will be v naught cos alpha, and the vertical component of the initial velocity will be v naught sine alpha. Now, with these two equations, d2x dt squared is equal to 0 and d2y dt squared is equal to minus g, the first conclusion that we draw is that dx dt, which is the horizontal velocity, is a constant quantity. And as such, with the initial condition at hand, we will find that x is equal to simply vx into t. And vx is the same throughout, so the initial value will be what it is all throughout. So Vx is V naught cos alpha into t. So that is the x is equal to V naught cos alpha into t. So that is the horizontal xt equation. What about the vertical equation? d2y dt squared is equal to minus g. Therefore, dy dt will be equal to, I mean, let me just here. d2y dt squared is equal to minus g, and dy dt is equal to vy. So dvy dt is equal to minus g. So vy is equal to minus gt plus a constant. I use always operate under the initial at t equal to 0, vy is equal to v naught sine alpha. Therefore, Vy is equal to V naught sine alpha minus Gt. That's the y velocity equation. You can see that the y component of the velocity depends on time, as opposed to the x component of the velocity, which is constant. The y component of the velocity has a linear dependence on time. And then this, by the way, is also, this is something that you discussed in your lab problem. Okay, and then dy dt is equal to vy, so you can solve for y as a function of t, and this is the with the initial condition that at t equal to 0, y is equal to 0. You are at the origin of coordinates. And so this is the y equation. Hence, you now have two equations of x and y, each of them depending on t. So x is a function of t, a linear function of t. Y is a parabolic function of t. So x and y individually depend on x is a function of t and y is a function of t. Okay. So what we will do now, so this is a parametric set of equation. X depends on t, y depends on t. If we can now eliminate t, then we can get an equation directly in terms of x and y. That is, so this is the point where we ended in the last class, the parametric equations. So t, let us go back to the x equation. T is equal to x by v naught cos alpha. That is what we write. T is equal to x by v naught cos alpha. So this is the t that we shall substitute in the y equation. I hope you are understanding the logic. So first we got a set of equations, x as a function of t, y as a function of t. And now the next thing that we will do is to eliminate t, substitute for t, and write x and y in a direct relationship with each other. So y is equal to v naught sine alpha. T is equal to x by v naught cos alpha. This is what we have. Minus g by 2, t squared. T squared will be x squared by v naught squared cos squared alpha. So v naught and v naught will cancel. Sine alpha by cos alpha will be tan alpha. And this will be minus g x squared by 2 v naught squared cos squared alpha. This is the equation of a parabola. Y is equal to x minus some constant. Y is equal to constant into ax minus bx squared kind of a form. Right. I mean, you have actually worked with this kind of system when you talked about the logistic equation. Of course, there you did not have y on the left-hand side. You had x dot. X dot is equal to constant into x, ax minus bx squared. So that was the equation of a parabola as well. So this is the equation of a parabola in the spatial coordinates x and y. And this gives the trajectory of a projectile without air drag. Okay. Let us see. If you see this equation, I'm sorry, this graph, this is y. Y is equal to 0 at 2 points, when x is equal to 0 and when x is a non-zero value here. So we can solve for that. So this distance, x is equal to 0 to where the projectile lands, is the full range of the projectile. So we shall look at that as well now. So when y is equal to 0, you said 0 over here, you get two solutions. One is x is equal to 0, x here, 0 here, and 0 here. Fine, that's a solution. But there's also another solution. The other solution is tan alpha minus half gx by v naught squared cos squared alpha is equal to 0. Therefore, x will be, solving for the second equation, it's a quadratic equation, so it must have two roots now when you set y is equal to 0. So one is x is equal to 0, and the other will be x is equal to, let us see, 2 v naught squared tan alpha into cos squared alpha by g. Now, what is tan alpha? Tan alpha is sine alpha by cos alpha. So one cos alpha and this cos alpha will cancel, and you will have v naught squared by g, 2 sine alpha cos alpha. And so 2 sine alpha cos alpha put together will give you sine 2 alpha. V naught squared by g, sine 2 alpha. That is the full range of the projectile, right? And it depends, as you can see, it depends on three things. First, the initial projection velocity. Second, acceleration due to gravity. And third, the angle of projection. So let's say that keeping the velocity depends on the firepower. Let's say you're shooting an artillery gun, right? Right now, a lot of that is happening in Ukraine. So you're shooting an artillery gun. So the initial muzzle velocity will depend on the firepower of your gun. So that is not something that you can control. It comes with the manufacturer's specifications. G, of course, you can't control. It's acceleration due to gravity. So the only thing that you can safely control or feasibly control is the angle of projection alpha. You lower the gun barrel, you raise the gun barrel, whatever. So that's the only thing on which you have an easy control. That's the thing on which you have an easy control, not the only thing. That's the thing on which you have an easy control. So under what condition will you get the maximum value of sine 2 alpha? Maximum value of the sine function is 1. So that will mean that 2 alpha will be 90 degrees. If 2 alpha is 90 degrees, then it means alpha is equal to 45 degrees. So when you make a 45-degree inclination without accounting for air drag, you will have the maximum range of your projectile. So that is what is that. The maximum range is V naught squared by G. Okay. Now, this is the thing that we shall have to work on numerically. That is, if you are asked to work on this problem on your computer by writing a program. I mean, so far what we have done is just we have done things by hand, integration and all that. All these things we have carried out integration, right? I mean, we haven't explicitly written integrals, but we have done integration all right, nothing else. Integral constant, as you can see. Now, suppose you are asked to integrate numerically, what will be your approach? Let us see. Uh, Here it is. You have got four equations to worry about now. Remember, follow carefully. This is fundamentally a second order system now. This is for the first time. So far, what you have worked on is dx dt is equal to fx, dv dt is equal to f of v, all these things, particle falling through a liquid column and all those things. Usually velocity equations, right? We worked with dv dt. So now we are looking at the spatial equation as well. Even in the bicycle rider problem, if you look at it, the bicycle rider problem, you just worked with dv dt equation. As you can see, the bicycle rider problem, here your equation was du dt, etc. Right? So this is the first order autonomous form. Now, for the first time, you are encountering a second order system. The second order system has its own range of new features and complications. We will discuss all that in the mathematical class later. But for the time being, we'll just have a simple approach. So you've got two second order equations. And each of them integrated once will give a first order velocity equation. So basically, you will now have to work with four equations. Let us see. Dx dt is equal to Vx, right? Vx is a constant quantity. Therefore, dVx dt is equal to 0. Okay, right. This is the actual equation of motion. dVx dt is equal to 0 along the horizontal direction. If that is so, then your Euler prescription is a very simple one. Delta V is equal to 0 into delta t, isn't so? 0 into delta t doesn't operate at all. Delta V is equal to 0. So basically, Vxi plus 1 is equal to Vxi. You have the ith value that is also equal to the I plus 1th value. This is a very simple prescription. What about the next thing? dvx dt is equal to 0, therefore dx dt is a constant velocity, Vx. This Euler, I hope you're following. This is not very difficult. This, on applying the Euler prescription, with which you are very familiar now, is what? Delta x is equal to Vx into delta t. But what is Vx? Every step you have to take Vx at I, but that is anyway a constant. So nothing to worry about. So the first two x equations are very simple. V is constant. Vxi and Vxi plus 1 are constants. So xi plus 1 is equal to xi plus Vxi, which is a constant, into delta t. It can't get any simpler than that. The complication comes in the y equation. Why is it so? Let us see. Let's look at the y equation of motion along the vertical direction. dvy dt is equal to minus g. Now you follow carefully. Now you will have to apply the Euler prescription twice. Uh, Delta V is equal to minus G delta T. Here is minus G delta T, and delta V will be Vy I plus 1 is equal to Vy comma I. Now you can see, because of this G delta T part, Vy comma 1, sorry, Vy comma I is not equal to Vy comma I plus 1. This equal to equality held in the horizontal direction, but not along the vertical direction. So you have this thing. You have to be a little careful. Next is that delta y is equal to Vy into delta t, and then in the Euler prescription you write it as y I plus 1 is equal to yi is equal to Vy comma I delta t. That is what you have. Okay, so these are the four Euler equations that you have to write. The x equations are very simple. You might as well not do this thing, but just for completeness, I have written this. I mean, whatever is happening at I is also happening at I, is the same value at I plus 1 for the x component of the velocity. But for the y component, that is changing. This will be a variable quantity. So you have to be careful. Every time you work with a y I, you'll also have to extract the value of y I plus 1, which shall then go be fed into the next iteration. That is how you will go about it. Okay, but these are four simple equations, relatively simple. Now what we shall do is that we will account for air drag. We have not. Parabola, I mean, projectiles don't travel through vacuum. They have to travel through air. And I have discussed this thing several times earlier that the resistance offered by air is not a small thing. In fact, particularly these things, these projectiles that are sent, they have to travel through. I mean, you can talk about ordinary artillery cannons. They don't send projectiles to great distances, maybe 50 kilometers or so, 100 kilometers at most, right? But what about missiles? They are also projectiles. You want to send Agni missile, ICBM, intercontinental ballistic missile. There, you have a target that you want to hit on the other face of the planet. Sometimes you may have to send your missile. I mean, these days there's a lot of threat about nuclear war stuff because of the Russian invasion of Ukraine. And so, if powerful nations engage in that sort of a war, then you will have to send projectiles to the other side of the planet. So you can immediately see the situation will be so complicated. Why? Because first of all, you'll not be talking about the launch from here and the target here separated by a flatter Earth. Here, for simplicity, we have chosen a flat Earth, but the Earth is not flat. If you want to hit a target on the other side of the Earth, then your range will be over the curvature of the Earth. So all those things have to be accounted for. And then ICBM, typically the missile has to go out of the Earth's atmosphere. They go out of the Earth's atmosphere and then they again have re-entry. And I told you that whenever something travels at a very high velocity through air medium, it encounters fierce resistance, so much so that the object can burn up like meteorites or meteors that enter the Earth's atmosphere. So you also have to have shielding technology. So those are very complicated matters. Missile technology is not a very simple thing. So that's why, I mean, these people are very smart people. Like, let's say, our former president, Dr. APJ Abdul Kalam. So he was the great master of these kind of technologies, right? So you can see, but we will just look at a very simple extension of this problem. It's a complicated problem, missile and rocketry, all these things. Here in Ahmedabad itself, you have an ISRO center. ISRO started from Ahmedabad, in fact. Now their headquarters have been shifted to Bangalore. But so you can see, I mean, these are not very simple things to it. It's not just like using your handheld catapult and shooting it in the air. So we shall now have to account for air drag, and that will cause a good deal of complication. First of all, there is no hope now of getting exact integral solutions like we have done over here, XY kind of equation, right? So you will not be able to get integral solutions now. So that is the reason why when you work on this thing in your lab, you have to be very clear about the correctness of your algorithm on this simple air drag free equations. Once you have done those things correctly, then you will have confidence that when you account for air drag, of which there is no integral solution. These numerical equations, these four equations written in terms of Euler, written by the Euler's method, can be verified by your analytical solution, can be verified with your analytical solution. But as soon as you account for air drag, there is no analytical solution to verify against. Be careful about that. Okay, also time step chosen and all those things, delta t, etc. You, by now, I expect you to have a clear idea of what the time step should be like, all those things. Those are matters of your judgment. Now let us just take a simple extension of this problem. Only air drag. We shall not go into all those curvature of our Earth business and difficult things. For that, one has to fall upon the expertise of ISRO. Okay, anyway, so here's the drag force. Drag force is minus bv squared. In the bicycle problem or in the parachute problem, we took the drag force to be, let me go back, we took the drag force to be proportional to square of velocity c. In this bicycle problem, minus meaning resistance, some constant quantity, into velocity squared. Similarly, fall of a parachutist or fall of something through air, I mentioned to you, it will be d will be proportional to v squared, gamma will be 2. So things moving through air, you can take square power resistance depending on velocity. So that is what we are doing. Um, so here we are. This is the projectile, y-axis and x-axis. I'm sorry, this is the grid, y-axis and x-axis. This dotted curved path is the path of the projectile. So along this curved path, this is the direction of motion of the projectile, and D opposes it. This arrow indicates the resistance to the motion, right? Let us say at some arbitrary point, the path of the projectile is given by this tangential vector, and it is making an angle theta with the horizontal axis and 90 degrees minus theta, of course, with the vertical axis. So the drag force, which is directed along this backward arrow, I hope you're able to see this thing clearly. It is directed along this backward arrow. This forward arrow is the motion of the projectile, and this backward arrow is the resistance due to air drag. That drag force has got two components. One is dx along the horizontal direction. It is d cos theta. D is the full drag force, and the other along the vertical direction, which is d sine theta. Well, actually, dy will be acting downwards. Don't forget that, and dx will be acting in this direction. So, because it's resisting the motion, right? So there should be two minus signs. I haven't written those minus signs. I'll do that. I mean, in the final equation, we will do that. So the horizontal component of the drag is dx is d cos theta. Theta is an arbitrarily changing angle now. For instance, at its peak, this tangent to the direction of motion will be horizontal. So theta will be 0 in that case. So cos theta, theta is a varying angle now. So cos theta is equal to, let us see, x component by the total velocity, right? Vx is the x component of the velocity, and cos theta is the x component of the velocity by the total velocity, and sine theta will be Vy by the total velocity. I hope you have not forgotten that. V is this, Vx is this, Vy is this. Vx is along the horizontal direction, Vy is along the vertical direction. So that way, we should be able to eliminate theta by writing it in terms of the velocity Vx by V, and for sine theta, it is Vy by V. But what is V? V is Vx squared plus Vy squared square rooted over. Nothing very challenging there, I hope. So what about the drag component? D is equal to minus B, where capital B, for simplicity, we are treating to be a constant, minus B into V squared. X component will be the, this is D. D will be minus B into V squared into cos theta. And cos theta is Vx by V, right? So this is D minus B V squared, Vx by V. Okay. And V squared by V will give you a single V, which is square root of this. Minus B square root of Vx squared plus Vy squared into Vx. I hope you have no difficulty understanding this. And likewise, dy, the y component of the drag force will be minus d minus bv squared into sine theta, which is Vy by V. V squared by V will cancel, and you will have minus b into square root of Vx squared plus Vy squared into Vy. Okay, so there we have these two equations. Now your equations of motion will be modified. Earlier, m dvx dt was equal to 0, and m dvy dt was only equal to minus g, right? Minus mg. But now we are talking about a force, so drag force, right? Not drag acceleration. So that's why for the force equation, we have put m. In the previous discussion, m did not matter because m would have cancelled out. So if I had put m over here, I would have put 0 into m. That would have been the same. I would have put m here, m d2y dt squared is equal to minus mg. Again, the two n's would have cancelled. But that's no longer the case now. So B contains information about the force. Okay, but anyway, earlier the right hand side was 0 and for the first equation, and the right hand side was just minus mg for the second equation. See, if you did not have air drag, capital B would be equal to 0. That's how you can use it as a switch parameter. Set capital B equal to 0 and you'll get the air drag free trajectory. Okay, but these two equations remain the same. dx dt is still the horizontal component of the velocity and dy dt is still the vertical component of the velocity. So now, as I'm saying, you can't really hope to get an integral solution of this equation. It's not a very simple thing to work with. Because why not? Because now you see you have got a Vx and a Vy mixed up here. Again, a Vx and a Vy mixed up here. Suppose you did not have Vy here, then you could have got the integral solution of this thing. It would have just have been square root of Vx squared, which would have been Vx. Vx into Vx would have been Vx squared. So m dVx dt would have been equal to minus Vx. So that would have been very simple. And similarly here, but now Vx and Vy are mixed up, so you can't really get an analytical solution by putting integral signs. Some of you have confusion about what I mean by analytical solution. This is an analytical solution. These two equations, solving for y exactly as a function of t, solving for x exactly as a function of t, using a pen and a paper, doing integrals, setting initial conditions, getting integral solutions, writing y as a function of t, x as a function of t. This is an analytical solution, right? And this is a numerical solution. This is a prescription for a numerical solution. Now, you can do the numerical solution in two ways. One, take small steps, small number of step sizes and do it by pen and paper using your calculator. That is something that is part of your mathematical theory exercises. But then in the lab, you can do the same numerical thing with the help of a computer by writing a program. So when I say analytical, I mean this. Be very clear. Next week, you have an examination. I mean this. When I say numerical, I mean one of two things. If you're doing by pen and paper, you do this thing and do by with the help of a calculator. And if you're in front of a computer, you write a program. That is the number crunching thing that we call. That is the real computational physics part, right? Computational, using a computer. Okay, anyway. So dx dt is equal to vx and dy dt is equal to vy. So dx dt is equal to vx and dy dt is equal to vy. These two equations are still the same. So if I were to apply Euler's prescription, applying the drag, accounting for the air drag, then the x and the y equations, x as a function of t and y as a function of t, will remain the same in the prescription, except that now vxi and vyi, vxi will also become a variable, and vyi was also a variable earlier, but now it will become a more complicated variable. So these two things, this was constant earlier and this was a simple linear function of t earlier, but now they will become complicated. So these two equations, x and y equations, are not to be changed. Their form in the Euler method. These two equations, the velocity equations, have to be changed. How so? Let us see. Sorry, here. What is the velocity equation? Delta v is equal to minus b by m into this thing, into delta t. So this is so in Euler's method, only the dvx dt and the dvy dt equation and dvy dt are modified as this thing. This is delta v. So vx comma I plus 1 is equal to vxi minus b by m vxi squared plus vyi squared into vxi into delta t, right? So that is what you have. Similarly, for the y equation, delta v is equal to minus g dividing throughout by m. Delta v is equal to minus g into delta t minus b by m into this whole thing into delta t. So this whole thing, when I write it in Euler terms, it will be vy comma I plus 1 is equal to vy comma I minus g delta t. M has cancelled in the first two terms. Then minus b by small m into square root of vx comma I squared plus vy comma I squared into vy comma I into delta t. So multiply by delta t in the last terms, this and this. So this is delta t, this is delta t, this is delta t. So basically, drag free, these two equations and these two equations. With drag, these two equations, x and y, but not these two equations. These two equations in x and y, and these two equations in vx and vy with air drag. Those are the only things that you have to do. So that is your theory of projectile motion, both without air drag, which is a very simple school level problem. This is something you learn at school, and now with air drag. I will just now go into some extra issues involving air and all that business. So one thing is, see, as I said, missile technology. I mean, when you are shooting an artillery shell doesn't have to go too far. Like, let's say, in the Kargil War, the Indian Army hauled Bofors artillery guns up the Himalayas, and then from there, they fired these Bofors artillery cannons on the Pakistani intruders on the other side of a hill. So the projectile did not have to go very high, but which means that from your point of firing to the maximum height, if the vertical height is not too much, then you do not have to worry about the variation of the air density, right? But suppose you're shooting an ICBM, then the ICBM will, let's say you're shooting it from your target over here, and your enemy target is somewhere on the other side of the earth, wherever. And so basically, your ICBM has to go out of the Earth's atmosphere. So even as you're going out of the Earth's atmosphere, air density is changing. So the drag force will significantly start varying because of variation of the air density, which we have not accounted here. We have not accounted for here. Now this constant B over here, we have chosen it to be a constant. But if you worry about the density of air and all that, then this constant B will no longer be a constant. For instance, it's a very simple example we took about up in the last class when we talked about bicycle motion. In bicycle motion, we talked about the drag force being proportional to C minus V squared. And then you have this whole package over here. What are the things? This is a dimensionless number. You have the density of air, right? Which we treat as a constant because you're traveling on the ground, and on the ground, the air density is constant everywhere. So we are treating it as a constant. But if you're shooting a missile to hit, that will go, an intercontinental ballistic missile that will go out of the Earth's atmosphere, and then the air density will change. Also, this is the area of cross section, but the area of cross section is not a big matter of concern in the way sense that these missiles are all using streamlined technology. You will see in these missiles being paraded during Republic Day, they all have very smooth, streamlined area of cross section. But the air density is treated to be constant. Air density is a very important factor these days. In fact, Russia, China, all these countries, America, they have developed hypersonic missiles. India is also doing that. Why hypersonic missiles? Because ICBM uh, takes some time. You launch it from your launch pad, it will hit the target, it will go out of the Earth's atmosphere, it will come down. All these things will make it visible to enemy radar. And so the enemy can intercept your missile by using interceptor technology. But hypersonic missiles do not travel at a great height. They travel close to the surface of the Earth, and they travel at a fast, very, very fast speed. Hypersonic, not even supersonic, much, much faster than the speed of sound. So you don't get much reaction time. So you don't get much time to intercept hypersonic missiles. So whatever it is, so you can see this drag constant, so-called drag constant capital B in our projectile problem is not really a constant. It's going to depend on various things, the air density being one of those. We shall not take up that thing in projectile problems. We shall not do that because, but as you can immediately see, the things that ISRO does or Dr. Abdul Kalam did, these were not very simple things. So that's why he was given the Bharat Ratna, made the president of the country. So this is the thing, this B that you see. I mean, when you do it in your, I mean, I will eventually ask you to work these things in your lab assignment, lab report. You will see for yourselves that without air, your missile is going at a great distance. With air, it'll just fall very close. And this projection angle can't be determined so neatly and theoretically here as we have done 45-degree. Your projection angle will also become different. So these are the things you can be a little bit of a missile expert by these equations. You'll see for yourself that air drag, I mean, just the drag force, the simplest form of drag force, and by simplest form, I mean that you can't even for the simplest form, you can't get an analytical solution. But even the simplest form of the drag force will tell you that missile technology is not a very, you want to get greater and greater range. How will you do that? So those are serious issues. I will not get into all those complicated issues. This is the end of your discussion on projectiles. I will simply go into discussing how air density varies. But this air density variation also has a bearing on how far your projectile can travel, right? Your missile can travel. So as I've written over here, the density of air affects projectile motion because the drag force depends on air density. Now let us see how air density varies. We will, but this is a general discussion. Although it has got some implications for projectile technology, missile technology, but the discussion that I will hold will have general applicability. So here it is. So here, let's say somewhere up in the atmosphere, you have got uh, a slab of air, right? Um, this is giving you air density. I mean, rho is the air density. Just a minute. Just a minute. I hope you can all see this thing, right? Can you please just confirm? Hello? Can you please just confirm, one of you?
Yes, sir.
Yes.
You can hear me clearly, right? Okay, thank you. Thank you. Okay, so here you have a slab of air. The density of air, I mean, this slab of air is at height Z, right? So the lower face, let's just, for simplicity, imagine that you've got a small rectangular box of air. And the box exists only in your imagination. A rectangular box of air. This is the cross section of the box. The box is projecting towards you, so you're looking at the box side on, right? This is the top face of the box. This is the bottom face of the box. This is the left face of the box. This is the right face of the box. The front face, you're looking at it here, and the back face is on the other side of the page, like that. Now, the box is considered a slab of air with a lateral cross-section area. So this is the area of bottom face area, A, and thickness is dz. This is the thickness of the box, dz, and the area of the top face and the bottom face is A, lateral cross-sectional area. And Z is the height from the surface of the earth. This is the Z height, right? Height is Z. And then this, from here to here, it's got a small height, dz. So the thickness of the boxes. So the air pressure above the slab is P plus delta P. You know that pressure changes as you go higher and higher. So at the bottom face, the pressure is P, and at higher, the pressure is P plus delta P. Note the plus. I have not written minus, right? Although we know that pressure decreases, but I'm writing plus. So the air pressure above the slab is P plus delta P, because I don't know beforehand whether air pressure increases or decreases, all those things. So I'm just writing that below it is P and above it is P plus delta P. That's the delta P is the change in the air pressure. So the air pressure above the slab is P plus delta P, and below it's P. Now, there are three forces acting on this box of air. What are the three forces? From below, this box is being held up by the air pressure. So these upward arrows are indicating the force due to the air pressure. So what will be the force from below? Force is, pressure is force per area. Therefore, from below, the force will be pressure into area, right? And above, the pressure is P plus delta P. So P plus delta P into this area will be the downward force, these downward arrows. So that's one. So there are, the air pressure above the slab is P plus delta P, and below the slab is P. Weight of air contained in the slab. So there are two downward forces now. One is due to the weight of this air contained in this box. And what is the weight? Air density multiplied by the volume multiplied by g. Weight, remember, is mass into g, right? M into g. So what is the mass contained in this box? Air density is rho rho into the volume of this box, which is A into dz, area of cross section A into dz, A dz into rho. That is what you have. Rho A dz is the mass of air contained in this box into G. Weight of air contained is m into G, so that is weight is downward. Also, this pressure is acting downwards on this face, right? So P plus delta P into A is the force, downward force due to the pressure, plus the weight. So the total downward force is P plus delta P into A plus rho A dz into G. So that is the total downward force that you have. Okay, total upward force is acting from bottom is PA. So between these two downward forces and this upward force, this air box is being held in its place. So the balancing that you will get is that the the upward force is PA, that is balanced by the downward force, which is P plus delta P into A plus rho A dz into G. Okay, and so you have some cancellations now. Let us see. PA is equal to P into A plus A delta P plus rho A dz G. Okay. PA here and PA here will cancel. Then this will be 0 is equal to 0 plus A delta P plus rho A dz G. So again, the A will cancel throughout, and you'll be just left with delta P plus rho G Z is equal to 0. Therefore, delta P is equal to minus rho G dz. As you can see now, G is a positive quantity. dz is this vertical height starting from here. It's a positive increase in the value of Z. Density of air is a positive quantity. So with a minus sign here, overall the right-hand side will be negative. So delta P is a negative quantity, meaning that as height increases, the pressure decreases. dz is positive, delta P will be negative. dz negative, meaning height decreases, delta P will be positive. dz will be negative, meaning minus, it will be negative with the minus sign outside, it will be positive overall, therefore pressure will increase if you decrease the height. That is what it is. Now what we shall do, we shall have to see how the density of air changes with height. So if you were a missile technologist, you'll have to account for the density variation in this so-called constant B. We have treated for simplicity to be a constant B, but density will be included in that B, and it is not a constant, as we shall see now. So what we do is that we approximate air as an ideal gas. As an ideal gas, which follows two prescriptions, namely that the gas molecules do not interact except for the occasional collisions among them. And all gas particles are point-like with a negligible total volume compared to the gas. Those are the ideal requirements for an ideal gas. For instance, if you have a cloud of electrons or a cloud of protons, they will not be an ideal gas. Why not? Because protons and electrons have electric forces of attraction and repulsion. But here we are talking about neutral gas molecules, like let's say O2, N2. These are neutral gas molecules. They being overall charge neutral, the only way they interact among themselves is by the collisions that they suffer, right? Otherwise, once collided, they leave apart each other. They don't exert any action at a distance kind of a field on each other, one another. So the gas molecules do not interact among themselves except for the occasional collisions among them. So that is one thing. And the gas has to be very dilute. What do I mean by very dilute? See, when you talk about a gas is a fluid that fills in all space that is made available to it, not like a liquid. If I give you a glass and you fill the glass with half water, the glass will remain half filled. But if I give you a container, closed container, and inject gas in it, it's not like that the gas will remain settled at the bottom half of the container and not go to the top half. That doesn't happen. The gas will fill the entire available space. And so basically, when you talk about a gas, you actually refer to the empty space plus the number of gas particles in it, right? Now, what happens is that if you have a very dilute gas, then the actual material particles, if you gather them all together in a tight ball or something, tight mass or something, the total volume occupied by that tight mass will be much, much smaller compared to the empty space in the gas, right? So ideally, we approximate this smallness of the total material component of the gas to be zero. How can we make a large number of particles occupy zero volume? Simply by saying that the particles are point-like, because a point is a zero-dimensional object. So you can have as many points as you like. All of them put together will still have a zero volume, but that is a mathematical idealization. So all gas particles are point-like with a negligible total volume compared to the gas, but that is an idealization, and that is why we say it is an ideal gas. So dilute gas whose molecules do not interact among themselves except for collisions among them. That is the requirement of an ideal gas, and air actually satisfies this requirement to a decent extent. So now what we shall do is that we shall have to work with this equation, because g is a constant, z is a variable, rho is a variable, because after all we are talking about variation of air density. So rho is a variable, z is a variable, p is also a variable. So we shall need a method whereby there are three variables in a single equation. We need to eliminate one of the variables, write an equation in terms of the other two variables. So what we shall do is that we shall have to find a way in which pressure and density can be connected to each other. And for that, we are going to the ideal gas equation. And what is the ideal gas equation? PV is equal to nRT. R is the universal gas constant, capital T is the temperature, V is the volume of the gas, and capital P is the pressure. Right, and so what about small n? Small n is the number of moles. Right, and number of moles, I refer to your knowledge of school chemistry. What is a mole? A mole is an amount of substance that contains Avogadro number of particles. Capital N, subscript capital A, as in Avogadro. And so, if um, you have Avogadro number of particles in a certain substance, you say that that is 1 mole of that substance, Avogadro number of particles, right? And so if you have capital N number of particles, that divided by Avogadro's number, which make up 1 mole, will give you the total number of moles in that, right? So that is what you have. So what we do is that we write the number of moles as the total number of particles divided by Avogadro's number, which is once again a universal constant. And so the right-hand side will be, so the V goes to the bottom of the right-hand side. So P is equal to RT by capital V into small n, but small n we are writing as capital N by capital NA. So capital N comes here for small n, and R divided by capital N A gives you the Boltzmann constant. We have discussed this thing earlier also when we talked about the fundamental constants. So basically here is what you have. P is equal to capital N, total number of particles divided by the total volume of the gas, into a fundamental constant, Boltzmann's constant, into temperature, the Boltzmann constant. Now, average mass of air molecules is m bar. Bar as in average, small m as in mass. Now, what is the air mostly made up of? Air is mostly made up of 90% hydrogen, nearly 90%, sorry, 90% nitrogen molecules, N2, and nearly 20% oxygen molecules, O2. I mean, nearly 80% and nearly 20%. Actually, it's slightly less than 80% for nitrogen and slightly less than 20% for oxygen, because there are also other gases like carbon dioxide, methane, the noble gases, all of those things are there in the Earth's atmosphere, but their percentage is quite small. So basically, you can take the average mass of air molecules to be a weighted average of 80% nitrogen. By the way, nitrogen has got an atomic number of 7, mass number of 14, nitrogen atom. Therefore, 2 nitrogens to make N2 molecule will give you 28 AMU as the mass of a nitrogen molecule. And for oxygen, it is atomic number is 8, mass number is 16. So O2 molecule will have a mass number of 32 atomic mass units. So 28, 80% of 28 and 20% of 32 weighted average will give you something like 29, 28.8, 29. Okay, anyway, so that is what you have. And so this equation, we are multiplying by m bar here and dividing by m bar. Okay, so if that is so, now what is capital N? Total number of particles in the gas. We are using air as an ideal gas. Total number of particles in air multiplied by the average mass of a particle. So basically N into m bar is the total mass of all the air molecules, right? Total mass of all the air molecules divided by V will be density of air. P is equal to rho into kBT divided by the average mass of an air particle, air molecule. So rho, as I have written here, is N m bar divided by velocity, right? So that is rho is air density, as has been written over here. Just have to squeeze all these points of information in. Now, so this is now your ideal gas equation of state. You started with PV is equal to small n RT, and now in terms of velocity, instead of velocity, you've got a new variable, air density. P is equal to rho into a fundamental constant Kv into T by another constant, which is the average mass of air molecules. Now, this is an important statement I'm making over here with an equation equation of state, right? With an equation of state having P rho T, we only have intensive thermodynamic variables. I'll just briefly touch upon this word. What do I mean by intensive thermodynamic variables? An intensive thermodynamic variable is one that does not depend on the system size. An extensive thermodynamic variable is one that depends on the system size. Let us look at PV is equal to nRT. N and R are not things we are worrying about. Oh, well, N we should, but let's not worry about that now. What is temperature? Is temperature an intensive variable or an extensive variable? Just think of this thing. You are sitting in your room. Your room has got a certain temperature now. These days are becoming slightly warmer, and the room also has air pressure, right? Now, if you suddenly decide to build a partition wall in your room, now you build the partition wall, but there will be air on both sides, and the pressure and the temperature of air in each half of the room will be the same as what it was earlier when there was no partition between the two halves. So basically, pressure and temperature are variables that do not depend on whether the system overall has been halved or not. Pressure and temperature are, therefore, not dependent on the system size, and they are known as intensive variables. What about the volume? Earlier, you had the full room, but now, as soon as you built a partition wall, then the volume on both sides of the partition wall are now half of what your original room size was. So volume depends on the system size. Therefore, volume is an extensive variable. Here, instead of volume, we have eliminated the volume. We have pressure and temperature and volume here. Here we now have pressure and temperature as earlier, but instead of volume, we have got density. Density of air can change, but the density does not change because of the system size, meaning that if you suddenly build a partition wall in your room, the one side of your room and the other side will suddenly not become any hotter or colder what it was earlier. Temperature does not change, and similarly, density of air will also not change because you will not have any difficulty breathing air on either on this side or on that side. So density also does not depend on the system size because density mass divided by volume. Mass is an extensive variable. Now that you've built a partition wall in your room, the amount of air contained in one half is half of what it was earlier. So mass is an extensive variable, volume is an extensive variable, but one extensive divided by another extensive gives an intensive variable. Density of air does not depend on the system size. You can have a small room, or you can go to a large hall outside, or you can go to the lawn, the garden, or the road outside. In different cases, your system size is changing. But that doesn't mean that you have any difficulty breathing the air that you have because the air density is not changing. So here you have an equation of state where pressure, rho, and temperature, pressure, density, and temperature are all intensive thermodynamic variables. But here you have volume as an extensive thermodynamic variable. This equation is important because when you have to deal with an open system such as the Earth's atmosphere, what is the volume of the Earth's atmosphere? There are no bounding walls. It's not like your room or a tin container or whatever. So whenever you're dealing with an open system like the world's atmosphere, like the world's ocean, it is always best to get into an equation of state where all the variables are intensive, such as this one. These variables do not depend on the system size, so you don't have to worry about system size, the effect of system size on your calculations. Anyway, so here we have one such equation. we treat the temperature to have a much smaller variation than density so that the temperature can be treated as almost a constant, which is not such a bad approximation really. I mean, on top of Mount Everest, the temperature will go down to, I don't know, on top of the large high mountain, temperatures will go down to, let's say, 0 degree or maybe a little less than 0 degree, minus 10 degree or whatever. A normal temperature outside on the close to the surface of the earth is about 30 degrees or whatever, but the density decreases drastically, right, compared to that. Uh, so basically, there are now, if I want to substitute for P here, in this equation, I shall have to worry about both the change in the density and the change in the temperature. So what we will do is that we shall approximate the temperature to have a constant value. In your theory problems, you'll be given a problem to work on where you can justify this treating temperature to be a constant. Anyway, that I'll discuss later. Now, so if T is to be treated as a constant, then KBT by M is a constant package. That does not change, only rho changes. Therefore, delta P is equal to delta rho into KBT by M. So this delta P will be substituted over here. Delta P is equal to minus rho G delta Z. And so delta P is this thing, and delta P is minus rho G dz also. So there you have this equation. So now you have density and Z as the two variables. T we are treating to be constant. Boltzmann constant, G and all those things are anyway constant. So we separate variables on two sides. Delta rho by rho is equal to minus m bar G rho, I'm taking to the left hand side, minus m bar G divided by KBT into dz. So you can see immediately delta rho by rho density by density, left hand side is dimensionless. So the right hand side variable Z is here. It immediately means that KBT by mg will be a length, will have a length dimension. dz divided by KBT by minus by m bar g will have will have the dimension of length. We shall see about that. Now we will integrate d rho by rho, starting from rho naught to rho, and this thing is a constant, minus mg by kbt dz, starting from the surface of the earth, z is equal to 0 to some arbitrary height z. And rho naught here is the air density at the surface of the earth, where z is equal to 0. So you integrate this thing, log rho minus log rho naught, d rho by rho will be log rho, is equal to minus m bar g z by kbt. Integration of this thing is very simple. Z minus 0 will give you z anyway. Therefore, rho is equal to rho naught into e raised to minus mgz by kbt. So immediately you will see if this z is a variable and it has the dimension of length, then m bar g by kbt must have the dimension of inverse length. I have discussed this thing many times earlier. Argument of an exponential function must be dimensionless, e raised to minus x. So what is its series expansion? 1 minus x plus x squared and all those things. So x squared, you can't add them if they have a dimensional dependence. Okay, there is an error here. It should be kbt by m bar g. kb is 1.38 into 10 raised to minus 3. That is correct. Temperature is 300 Kelvin. I'm taking that's room temperature. There's an error here. I've taken m bar to be 10 raised to minus 27 kg. Well, actually, the mass of a proton or a neutron is 1.67 into 10 raised to minus 27 kg. But here, the average mass is the mass of a nitrogen, the air molecule. Air is 20% oxygen and 90%, 80% nitrogen. So that weightage should also have a factor of something like 29 or 30 over here. So if I were to have divided this thing by 30, so m bar should be something like 30 into 10 raised to minus 27. I overlooked that 30, and so I got this 300 kilometers. It should actually be divided by 30, and therefore you should have 10 kilometers. In the set of corrections, I have mentioned this thing. I will touch upon that thing later. So the scale of Z is not 300 kilometers. The scale of Z is about 10 kilometers. But that's also quite a high value because Mount Everest is less than 9 kilometers. So basically, this Z will be much less than 10 kilometers for our practical purposes. And so you can just apply, if you say Z is much less than this thing, then you can write e raised to minus m bar gz by kbt to be equal to 1 minus m bar g by kbt into z, right? So kbt by m bar g will be much greater, something of the order of 10 kilometers as with respect to z. M bar g by kbt, or kbt, sorry, kbt by m bar g will be of the order of 10 kilometers. So z is typically much less than that. And so you can say that since this thing is small, I can neglect the higher powers. Otherwise, you'll have to account for the higher powers. So this is the, anyway, this is the general formula. This is the way air density depends on height. Rho has got an exponential, rho decreases exponentially with z. But if z is much smaller compared to the scale of height, which is about 10 kilometers, once again, I'm asking you, advising you to overlook this value of 300 kilometers. It should be divided by 30, so it should be 10 kilometers. So if that were to be so, then you can approximate this density function by a linear formula. Rho is equal to rho naught 1 minus m bar g z by kbt. So this kind of approximation holds good when z is very much less than kbt by m bar g. In that case, in the series expansion, the higher powers can be neglected. So that is the way the density varies. So as I said, in projectile motion, there are various things that you have to worry. One is also the variation of air density. We have just discussed that thing now. So yeah, I mean, there's one last topic I shall touch upon. We have about 15 minutes, and I shall also take 5 minutes extra today. Please bear with me. So what about turbulence in the atmosphere? In the one of the last classes, I discussed that the atmospheric viscosity that you have, just like diffusion. Diffusion is when you want to, let's say, melt sugar in your coffee or tea. So how do you do that? You don't just wait for the system to happen in its normal course of things, for the process to occur in a normal course. You use a spoon and stir the coffee. When you stir the coffee, uh, diffusion is enhanced. Similarly, in the case of air, so basically when you stir the coffee, you're creating turbulence in the air, in the coffee, and that will bring about greater diffusion of sugar. Similarly for viscosity. Viscosity is a property of the liquid. Viscosity is a property of a fluid. But in the case of a fluid like air, in liquid, there is an appreciable viscosity, but air is very thin. So air does not have much natural viscosity of its own, but the fact that there is turbulence means that this resistance to anything is enhanced because of turbulence. So let us see. Turbulence in the atmosphere can also affect the motion of a projectile. Let's see, in order to do so, let's try to understand streamline motion and turbulent motion. This is a little diagram. You have experienced this thing in your basin tap or your bathroom tap, whatever. You open a tap. If the flow is small, then you will see that the water that is coming out has got a clear profile. You can see clear, transparent water. But if you increase the flow velocity, then the clarity through which you can see, with which you can see through the water is gone, and it falls down in a white foaming stream. In the former case, when you have a clear view, you have streamline motion. So all the water molecules are falling in uniform with you in a nice, well-defined paths, trajectories, smoothly, and this is known as laminar motion, smooth and laminar motion. But as velocity increases, the water molecules will go chaotically. Water molecules start moving chaotically, so the motion becomes random and chaotic. That is turbulent motion. So when you see the water stream coming out of the tap to be white, not clear, so you know that turbulence has set in. You can also have this thing. Suppose you have a tap that is placed at some height above the ground. You open the tap, even with a slow stream, the initial part of the flow will be clear, but as it is falling under gravity and velocity is increasing with higher and higher velocity, the motion will become turbulent. So the top part of the falling water column will be clear, but the bottom part closer to the ground will become white, right? So when you have high velocity, you have turbulent motion. As you can see that these water molecules are chaotic and all these things. I mean, this diagram is chaotic. So anything that is trying to move through this will encounter greater resistance than trying to move through this. Just like you will have a good deal of difficulty trying to move through a chaotic mob. But suppose soldiers are marching smoothly forward, you can find your passage in a gap through two marching columns and you can move forward. So this thing does not offer much greater resistance as compared to this thing. So turbulent motion, turbulence in the atmosphere also offers resistance to anything that tries to travel through the atmosphere. I just gave you some simple examples. Now, there is one equation. I'm not deriving this thing. It comes from fluid equation known as Bernoulli's equation. That's got a good deal of importance in fluid mechanics. Bernoulli's equation says that v squared by 2. By the way, if you were to multiply this whole thing by m, you will immediately see it will be mv squared by 2 over here and mgz. And what is mv squared by 2? Kinetic energy. And mgz is the potential energy for a single particle. But in the case of a fluid, we do not refer to a single particle. We refer to the fluid medium as a whole. So we take a specific equation meaning per unit mass. So you divide throughout by m, and this is the equation that you get. I'm just giving you some ideas of this thing. I have not derived this equation. So let us say at a particular height. So v is the velocity of the fluid, p is the pressure of the fluid, rho is the density, and z is the height. At a particular height, z is constant. So this equation explains the lift of an aircraft. The lift of an aircraft is like what? Let us see. Here, this is the wing cross section. I hope you know that the aircraft, when it flies, when a aeroplane flies, there are four forces acting on it. One is gravity, which is trying to pull it down. The other is the lift that is acting against gravity to keep it in its place. And horizontally, there are two forces also. One is the air drag that is resisting the aeroplane's forward motion. And the other is the engine thrust that is pushing the plane forward. So there are four forces acting on an aeroplane. We'll just be worrying about the two vertical forces. Okay. So it should be falling under gravity, but it doesn't. Why not? Let us see. There is a here I have drawn the wing cross section. You notice that the lower face of the wing is flatter compared to the upper face. The upper face has got a hump-like profile. Now, if you travel through above the wing, closer stream, let's say that the air is the air is cool, and you have got smooth streamlines. So your plane wing will be cutting through these air streamlines, right? So with respect to the plane wing, from the point of view of the wing, it is as if that the air molecules, air streamlines are going in the opposite direction. Viewed from the reference frame of the wing, it would look like that, right? I mean, the air does not have to move, but the plane is moving through the air. So from the point of view of the plane wing, the air is going in the opposite direction. Now, because of this extra hump-like structure on the top face, the streamlines would be forced to come closer, right? If there are more streamlines here, then they will be bunched up close and they would want to move out more quickly. As a result, the upper part has got a higher velocity as compared to the lower part. Here, this face is flat and these streamlines are going in the opposite direction, but they are not bunched up very closely. Here, they are being bunched up very closely. So these streamlines don't want to be bunched up. So as we want to bring them closer, they will be moving out more quickly. Okay. So if that is what is happening, then here it is. Above the wing, closer streamlines have higher velocity. Now let us refer to Bernoulli's equation. Below the wing, the streamlines have lower velocity. Hence, at nearly the same height, the pressure is higher above, right? I'm sorry, pressure is higher below. So this plane wing does not have too much of a thickness. The plane itself is flying at a speed of, at a height of, let us say, 30,000 feet. So the thickness of this wing is not too much. It wouldn't even be 1 or 2 feet or whatever, something of the order of barely a few feet, 1 or 2, 3 feet. So you can treat this and this to be nearly at the same height. Therefore, what are the other two variables? Velocity squared velocity and pressure and density. But at this same height, density is also nearly the same. So Z and rho can be treated to be nearly the same both above and below the wing. Right. So what changes now? Velocity is higher above the wing, velocity is lower below the wing. So if velocity is higher, v squared plus p by rho is to be, p is not a constant, v is not constant, but rho can be treated to be nearly constant, z can be treated to be nearly constant. So basically, it's now balance between v squared by 2 and p, right? So if v is higher here, p will be lower because the two of them added up is a constant quantity. And if v is lower here, then p will be higher here. So basically, the pressure below the wing will be higher compared to the pressure above the wing. As a result, there will be a net lift because of this thing. This is being governed by Bernoulli's equation. By the way, you can also think of why there should be a higher velocity, because these streamlines are starting at here at the same point and they also are meeting at the same point. But here they are having to travel, they are being made to travel a longer path. It's not completely an accurate point of view, but you can imagine it to be like that. But they start at the same point, they meet at the same point, but here the streamlines are nearly flat, but here they are being made to travel a longer distance. If they are being made to travel a longer distance, they will have to do so in quicker time to meet the bottom streamlines at the same point here. If that is so, then they will have to travel faster because they have to travel faster, but they have to meet their friends at the same time, so they have to travel quicker. Anyway, the whole idea is that higher velocity above the wing, lower velocity below the wing. As a result, higher pressure below the wing, lower pressure above the wing. As a result, you get a lift from this thing. But suppose you have turbulence, then all this streamline structure is lost. As a result, this thing doesn't work when you hit a turbulent pocket, air pocket. Turbulence can also cause velocity and pressure difference in these objects, right? So that is something that you experience as soon as you enter a zone of turbulence in the monsoon season and those times when there is a lot of churning about in the air. Winters are much cooler, you don't get those things. But in the monsoon season, when a plane flies into a turbulent zone, then you will see upheavals, up and down motion. This whole business of a smooth balance due to higher pressure below and lower pressure above will not hold because the air is no longer following smooth laminar paths. They will be chaotic. They will be going this way or that. So in turbulence, you have that sort of a thing. By the way, in cricket matches, you also have those things. How does a cricket ball swing in the air? How does a cricket ball swing in the air? You will have seen that fast bowlers, they polish the ball on one side and they keep the ball rough on the other side of the seam. A cricket ball has a seam, right? And so one side is kept polished and the other side is kept rough after some use. So let's imagine a cricket ball and the ball is traveling through air. All good fast bowlers, some of you, if you play cricket or follow the game, know that all good fast bowlers try to make the ball land on the seam so that you have the smooth face of the ball on one side vertically and the rough face on the other side. Now, the air traveling against the ball, so from the point of view of the ball, air is traveling on both sides of the two faces, both sides, against both faces. Now, against the smooth face, the ball will have, the air will have smooth streamline flow. Against the rough face, there will be a little bit of local unevenness in the flow. I'm not using the word turbulent, although you'll see in monsoon season or if the air is moist, such as happens in England, the ball swings much more as compared to dry Indian conditions. Now, what happens is that the air next to the rough face has got a smaller velocity because it is undergoing all this rough motion, right? So the pressure on that face, height will be the same on both sides of the seam. Z will be the same. Rho is also the same at the same height. So next to the rough face, the velocity is less, and therefore the pressure will be high. Next to the smooth face, the velocity is more, therefore the pressure will be less. So there will be a pressure difference on the ball on its two faces on both sides of the seam. As a result, because of the pressure difference, there will be a lateral movement of the ball. So basically, it's the same principle that is being applied. Just to give a lift of an aircraft, just for general knowledge, I've referred to this lateral swing of a cricket ball. So, as I said, these things have a good deal of significance for projectile motion. I have not discussed this thing in detail. I've just talked about two things, namely density variation of the Earth's atmosphere and turbulence in the Earth's atmosphere. Those two things will have a good deal of bearing in your projectile missile, guided missile technology. So this B that you have taken to be constant will account for all those things, and B will no longer be a constant. Anyway, I don't want to extend the academic discussion. I have come to the end of this discussion up to page 23. This is the last page. This will be a part of your examination. Please just bear with me. I will still need some discussion. So to hold, so this completes your exam syllabus. Your exam, I'll stop the sharing, by the way. I'll stop the sharing. Please just bear with me. I'll need a few important instructions to be issued now. See, I will send you your exam syllabus today, and I will also upload your recordings. I have uploaded lecture 8 and 9th, right? There were some issues with lecture 9th, so that's why I couldn't upload it sooner, but the system administration staff has helped resolve that issue over here. I'm stopping the recording now, by the way. The system administration staff